All right, good morning, guys. Today we're going to be covering 7.2, the Pythagorean theorem, and space figures. So Pythagorean theorem just being a squared plus b squared equals c squared. We've seen it before. And then when we say space figures, that means that we're going to be talking about figures in three-dimensional space. We're going to be focusing in on two of them today. One of them is a rectangular solid, the other being a regular square pyramid. So let's go ahead and get started by focusing in on different parts of each. So on the left side here, we see that we have our rectangular solid. We call it that because each side is a rectangle. And within that, we have a few different vocab words. So each side we call a face. It's facing the outside. So FBCG, this plane here, that is a face. And again, we have 6 of those along a rectangular solid. Now, where the faces connect to each other, that's called an edge. So the edge is where all the faces connect. And there's going to be 12 edges. So we see that there's 4 edges on bottom, 4 edges on top, and then 4 edges for our columns. Lastly, we have diagonals. Diagonals go from one point all the way through the solid. So the diagonal of a solid goes from H to B, from D to F, A to G, and E to C. So those are all of our diagonals, and that's what we're going to be finding a lot of today, so to keep that in mind. The other solid that we're going to be dealing with is a regular square pyramid. It's called a square pyramid because the bottom of it is a square. And then it's a pyramid because all the triangles will meet at a single point. It's very important for pyramids. Pyramids will always meet at a single point at the very top. That's different from a triangular prism. So that's the big distinction. Pyramids will meet at a single point. Now, in a pyramid, we have a few different vocab words. The most common one that we have and that we should already know is the altitude. The altitude goes from the very top of the pyramid and goes straight down and intersects the base at 90 degrees. It's the altitude that is the true height of this figure. So if I want to know what the true height is, if they're asking for the height of a pyramid, it's always going to be the altitude that we look for. We also have a base down here. The base is the bottom. It's the square. So if they ever mention the base, it's always where the bottom is. Because again, we build from the base and then we build upward. So the base will always be at the very bottom. Lastly, we have slant height. Slant height is just the height of the slant of the pyramid, the side of the pyramid. So it's going from the very top, and it's going down the edge, down the slant of it, and it intersects at 90 degrees at the very bottom. So it intersects segment KM at 90 degrees. That's where we see that 90-degree intersection, which will be very useful because then we have another right triangle to use Pythagorean's theorem. Now, going back to this rectangular solid, again, we have 6 faces, 12 edges, and 4 diagonals. And if I were to draw a net, and a net is just taking this figure, and since it's a box, it's just breaking it apart and laying the box out. So if I were to break this apart, you would see that it looks something like this. And of course, if I were to fold along each of these edges here, it would fold back into this box, this solid. So this is called a net. Nets are extremely useful. You're going to see them a lot as we move forward in this class, but just know that this is called a net. And again, we see that we have our 12 edges here. We have our 6 faces, and then we have our 4 diagonals. So I just want to make sure that we see a net for the first time. Again, it's just taking the box and ripping it apart, just like you'd have to do if you were to take it out to the trash can or something. All right, so let's go ahead and work on a couple problems. And again, we're going to be looking for the diagonal quite often with these. So just keep that in mind whenever we're dealing with a rectangular solid. So here's our first one. The dimensions of a rectangular solid are 3, 5, and 7. We want to find the diagonal of the solid. So here the diagonal would be HB. Now if I'm trying to find the diagonal of a face, that would be DB, and that'll be useful for us as well. So for this, the first thing that we need to do is we need to identify that what we're looking for. And again, we identify that as HB. So if I want to find HB, I see that it has a right triangle HDB. So I need to have the other two legs. Well, I have HD. HD is just 5, because since it's a rectangular prism, opposite sides will be congruent. So if HD is 5, I just need DB. And then I could use Pythagorean's theorem for it, but we don't have DB. However, I see another right angle making a right triangle over here with triangle DAB. So therefore, I can use triangle DAB in order to solve for side length DB. Using Pythagorean's theorem, again, let me just go ahead and label up these so that we see them a little bit clearer. Using Pythagorean's theorem, we'd have a squared plus b squared equals c squared. So 3 squared plus 7 squared equals db squared. 3 squared will give us 9. 7 squared will give us 49. And combining those like terms, we'll be left with db squared equals 58. From here, let's go ahead and take the square root of both sides. Doing so will give us db is equal to the square root of 58. And if I were to try and simplify this radical, try and write out our factor tree, it doesn't break all the way down. It stops at 29 and 2. So since it doesn't break all the way down, we're just left with radical 58. Now, I'm not going to actually simplify this radical into a decimal quite yet, because I need it for the next part. If I were to be at my final answer, then I would take this as my final answer and round it to the nearest tenth. However, we need it for the next portion, so we're not actually going to we're not going to round this or anything. We want the exact answer still, or else it'll throw off our final answer at the very end. So, at this point, we now have dB, we have HD, now we can find our diagonal HB. So we have 5 squared, So again, HB is our diagonal, and for our Pythagorean theorem, we now have 5 squared plus radical 58 squared equals HB squared. 5 squared will give us 25. Radical 58 squared, the radical and the square cancel, leaving us with just 58, equals HB squared. Combining like terms will give us 83 equals HB squared. And then to get rid of the square, we can take the square root of both sides, giving us HB is equal to radical 83. If we were to enter in radical 83 on our calculator, we'd be left with about 9.1 units. Again, this is what you guys would be entering in on your homework because we want it rounded to the nearest tenth. But for an exact answer, you'd say it's radical 83. So again, the measure of the diagonal is radical 83 units. All right, next up. Given the regular square pyramid shown with altitude AG and slant height AF, the perimeter of BEDC, so the base, is 40, and AC is 13. We want to find BC, the slant height AF, and the altitude AG. Let's go ahead and start with BC. So I know that we have a square pyramid, meaning our base is square. And the perimeter of that square is 40. Well, since we have 40 and we have 4 congruent sides because it's a square, we can do 40 divided by 4, giving us 10 units per side. So each unit has 10 in length. Next, we need to find AF. Well, AF is our slant height. And I know that our slant height intersects BE at 90 degrees. So this angle here is 90 degrees for triangle ABF. And that's the triangle that we're going to use. Now, since AC is 13, AC will also, since AC is 13, AB will also be 13. We're trying to find AF, which is one of the legs. And then for our other short leg, we have a length of 5. Now the reason for that is AF intersects at the midpoint. And if the whole length is 10, that means that half of it would be 5. So therefore we would use Pythagorean's theorem as AF squared plus 5 squared equals 13 squared. Again, we're looking at triangle AFB. Solving Pythagorean's theorem here will give us AF squared plus 25 equals 169. And subtracting 25 from both sides will leave us with AF squared equals 144. Lastly, if I want to get rid of the square so that AF, our slant height, is all by itself, I'm going to take the square root of both sides, leaving us with AF equals 12. Now, it's only going to be positive 12 because we're dealing with distance, and we know that distance can't be negative. So now we have AF is 12, and that's really important for us because that will allow us to solve for AG. So now, in triangle AFG, we have the hypotenuse as 12. We can find FG, same reason that we found BF, and then we're trying to solve for AG. So FG will be 5 units, because again, the altitude is going right to the center of the pyramid, right to the center of the square. So therefore, from the edge to the center would be 5 units, because the whole thing is 10. The whole edge is 10. So therefore, we have 5 squared plus AG squared equals 12 squared. Again, looking at this, we have 5 here, AG, and then 12. And again, our hypotenuse, always opposite the 90-degree angle, our hypotenuse here is 12. So that's why it's on one side. Solving for AG will give us 25 plus AG squared equals 144. Subtracting 25 from both sides will leave us with AG squared equals 119. And then to get rid of the square, again, we take the square root. The square root of AG squared is just AG. The square root of 119 cannot be reduced, so we're left with AG equals radical 119, which is about, and this is what you'd put in your homework for an answer, which is about 10.9. So it's 10.9 units long. So now we have BC, AF, and AG. Again, these are the two types of example problems that you guys will be seeing on your homework. Again, the first one being the rectangular solid, the second one being the regular square pyramid. All right, let's go ahead and try out a conceptual problem to finish this off. So, in the cube, find the measure of the diagonal in terms of x if AB equals x. Then the second part, if AC equals x. So getting started, I'm going to assume that AB is equal to x. And since this is a cube, each side is a square. So all sides are going to be congruent here, except the diagonals, of course. So if AB is equal to x, then AB is x and BC is x. And I can find the diagonal of this bottom square as AC using Pythagorean's theorem. Now what we're looking for, since we're looking for the diagonal of the solid, we're looking for from point A all the way up here, and I'll go ahead and call this point D. So we're looking for that length. So I first need to find AC. To find AC, I'm just going to replace these with their variables. So I have x plus x equals AC squared. And again, these should both be squared as well. So x squared plus x squared equals AC squared. Combining like terms will give me 2x squared equals AC squared. And the squared should be popping up in just a second. To get rid of the square, we take the square root. This will leave us with AC equals x radical 2. And the reason for that is because we get 2x squared, which is the same as 2 times x. I have a pair of x's, so I can take them out of the radical, leaving us with x radical 2. From here, we can find out AD now. So I know that this is x radical 2. So AC is x rad 2, and then I know that DC is just x, because again, all the sides are the same within a cube. So therefore, we'll have our two other sides, x squared plus x radical 2 squared equals our diagonal squared. From here, we can just go ahead and solve. X squared will stay the same. I'll just bring it down. This x radical 2 squared, this will turn into 2x squared. It'll turn back to what it was before I took the square root over here, which makes sense. I'm squaring the x, and then the square root sign and the square cancel each other out, leaving us with 2x squared. Combining like terms, because they have the same variable and exponent, will give us 3x squared equals our diagonal. Our diagonal squared. Don't want to forget that square there. And then from here, to get rid of the square, we take the square root of both sides, leaving us with x radical 3 is equal to our diagonal. Now again, the same reasoning applies. We have 3x squared prior, which is the same as 3 times x times x. We have a pair, so we can take it out. So what that means is that no matter what side they give me on a cube, if they said, oh, one of the side lengths is 6, well, then the diagonal is equal to 6 radical 3 for the solid. So again, you'd be able to determine any side, any diagonal based upon just the side lengths of a cube now, which is very useful for us. Let's go ahead and try out letter B next. Letter B, this time we're assuming that AC, our diagonal, is x. Well, the first thing that we're going to do is we need to solve for the side lengths here. So since this is a square, the diagonal creates two 45, 45, 90 triangles. So there's one over here with ABC. There's one over here on the other side, just due to this diagonal. Now I drew up my 45, 45, 90 triangle, and I know that my hypotenuse, the longest side, that's equal to x. And within the 45, 45, 90 triangle, it's usually equal to y radical 2. So I'm going to go ahead and set that equal to x, and I'm going to go ahead and solve by dividing both sides by radical 2. The radical 2's will cancel, leaving us with AB, the side lengths, are equal to x over radical 2. Now again, I want to continue practicing because we don't want radicals in our denominator. So we need to rationalize this denominator. To do that, I'm going to multiply both the numerator and the denominator by our denominator, radical 2. So this will change into x radical 2 over 2. The way that we got that, I just multiply straight across. X is on the outside of the radical, so it stays outside. So it's x times radical 2, giving us x rad 2. And then radical 2 times itself, that's the same as squaring it, meaning the radicals disappear, leaving us with just positive 2 on the bottom. Which means that all of our side lengths are x rad 2 over 2. So I now have both of our legs. X rad 2 over 2 is one of our legs. Our other leg is just x. So now we can use Pythagorean's theorem to find our diagonal. So this will give us x squared plus x rad 2 over 2 squared equals our diagonal squared. From here, I'm going to go ahead and focus in on the blue first. I'm squaring everything in there. So the squared goes to the x, giving us x squared. Radical 2 squared, well, that just cancels. And then 2 on the bottom, that squared will give us 4. So we now have x squared plus 2x squared over 4 equals our diagonal squared. We can reduce this fraction down. We can reduce it down to 1/2. So that'll give us x squared plus 1/2 x squared equals our diagonal squared. Combining like terms, 1x squared plus 1/2 x squared will give us 3/2 x squared equals our diagonal squared. Again, 3/2 is just the same as 1.5, so keep that in mind as well. From here, we want to get rid of our square, so we take the square root of both sides. Doing so, we'll cancel out the squares on both, leaving us with our diagonal is equal to x times radical 3 over 2. Again, for our radical, just so that we can see it, it's the same as 1.5 times x. Let me do this. Times x times x. We have a pair of x's, so they can go outside. The 3/2 stays on the inside. And that is our final answer. All right, so we have now covered everything for the Pythagorean theorem and space figures. So again, you're going to run into these two space figures. We'll be covering more three-dimensional figures coming in the next unit or so keep that in mind. But other than that, just make sure that you guys ask any questions, contact me if you need anything. Thank you guys for watching, and if you need anything, please let me know.